Okay, so
Yeah.
thank you, Chairman. So I'm Tsutomu Nagatsuma of NICT Resilient ICT Research Center. So today I'd like to introduce about agriculture training via visual IoT technology. We have developed remote training system under the collaboration of some companies and universities with great support from Kami Agricultural High School. Then this is a background. As you know that in practical education, such as agriculture, training is emphasized in the same way as classroom lectures. Real training is an essential way to transfer tacit knowledge from the teacher to students, so that the field work is very important for agriculture. However, the COVID-19 situation occurred since 2019 has caused difficulties in real training. Due to its characteristics, it was difficult to avoid the 3CS, so the real training was canceled or reconsidered. This is some news on the internet in the Japanese news, suggests that some of the agriculture universities and also the high schools faced on the difficulties for the real training. So we need to solve this problem using information and communication technology. So that the remote training system via visual IoT technology is needed for solve this problem. So if we consider realize the remote training with transferring the tacit knowledge, two key elements for realization of remote training for transfer of tacit knowledge it's important. The one is the realism of transmitted video information. This is strongly depends on the image resolution. So the higher resolution images provide a realism rather than the lower resolution. And the second one is the immediacy of video information corresponding to synchronic communications. So it strongly depends on the speed and bandwidth of the network and the characteristics of the protocol used. So we can satisfy the two elements if we can use high-speed broadband and highly stable network environment, such as fiber network for remote training. However, such ideal network environment cannot be available in vast farmland in the suburbs. The realization of high quality and low latency video transmission in the 4G LTE mobile communication environment is an issue of remote training. And I'd like to review the current technology here. And one key point, realism of transmitted video information is available by viewing recorded or stored high-definition video content. But there is no synchronic communication. So maybe we can always watching the YouTube or some Amazon Video Prime or such kind of high-definition video content, but it's not realize a synchronous communication. The second point, the immediacy of video information corresponding to synchronic communication. The immediacy of video information corresponding to synchronous communication has been realized by commercial teleconference tools. It's very popular now, but the resolution of the transmitted video is quite low and the realism of the video information is poor. So we need to develop our own system for agriculture remote training with satisfying these two key elements. And it's also concerning to the wireless, under the wireless network circumstances. And this is the concept of agriculture training by a visual IoT technology, which we call APAN. So the left side, for remote training, only one student or teachers is in the field with cameras and IoT sensors. The rest of the students and teachers in classroom or home and communicate with the student in real training via visual IoT technology. So we need to prepare the video transmission component and the reception component. To realize high quality and low latency video transmission in the mobile communication, we select HPVT protocol, which is resilient for low latency data transfer. This is the components of APAN. The left side photo shows the transmitting component, which consists of video camera and Raspberry Pi 3 board, and mobile communication unit and mobile battery. And receiving component is on the right-hand side photo, and this is a display and mobile communication unit and Raspberry Pi 3 board and mobile battery. So that the component of APAN is quite cheap and compact. So it's convenient for the mobile environment to provide a remote training. And I'd like to introduce a demonstration experiment of remote agricultural training. Last October, we have done the experiment as a task-based learning. This time, Kami High School students conducted remote training to Shikama Junior High School students. So the Kami Agricultural High School student play a role of teacher, and the Shikama Junior High School student plays a role of students. Video transmission devices and reception devices have been installed at both Kami and Shikama, and enabling mutual HD video transmission via mobile communication. Web conference system is also used for voice communication. Web conference remote training can be watched remotely by the reception device from NICT Sendai and Kogani for monitoring. The contents of remote training are planned and drafted by students of Kami, and the system is set up and operated by them based on the manual prepared by ourselves. Now, I will show the movie of the experiment as example. This one. This is a video at the Shikama classroom, and the teacher that reported the situation at classroom to the farm, and the high school student now teach training to the Shikama student. And one of the great situation is that, as you can hear, lots of students are quite excited to see the quite beautiful images are sent from the farm, and that situation suggests that we succeeded at two-way real-time video transmission in HD quality via mobile communication. Okay. So after demonstration experiment, we have asked students who joined the experiment to fill out the questionnaire like this. And this part is the summary. According to the impression of participating in remote training, about 19% of the students answered the training was good. And more than half of the students responded that they would participate in the training again. And they also feel that the visuals and audio was generally well received. And according to the impression of plant cultivation, more than 60% of the students answered that they understood well how to report plants. The number of students who want to grow plants in the future has increased after remote training. And these results show that the remote training gives positive impression to students, and we were able to provide good learning effect via our remote training system. So in summary, the remote agricultural training system that we have developed was succeeded in two-way real-time video transmission in HD quality by mobile communication. We pioneered the possibility of using this system to remotely teach training in practical fields such as agriculture. And by using this system, we are freed from the geographical and spatial restriction of the training site and the learning site. It also expands the possibility of a new type of training that does not exist, such as comparative studies among agriculture high schools and remote agriculture training to foreign countries and so on. That's all. Thank you for your attention.
Wow. Yeah, interesting. Thank you very much. And any question from the floor? Okay, not I have. Okay, the minimum bandwidth that for your system to make it work. So what is the minimum for the because you all have the 4G, 5G already, but for the system to work stably, what do you need?
Yeah, actually, our HPVT protocol, it is quite resilient protocol to transfer image. So if the bandwidth is quite poor, then this protocol optimize the size of the data, and then if we use the lower bandwidth, then the protocol transmits a low resolution images, and then we don't interrupt the transmission, and that keep going for the low latency.
Okay, because with this is like from the Dr. Ken Murata.
Yes.
His system is like need kind of high resolution and higher bandwidth communication in order to capture the video into his algorithm, the movement algorithm or the flow algorithm. So so this one can be integrated into that too. This one can integrate into the system that Dr. Ken working. Is it?
Yes. As you can see that he's also the collaborator of this
project.
Right.
Okay. Yeah. Oh wow. Yes. And below. Sorry. Small.
Sorry. This time I just put my name bigger, but he's also the great contributor.
Sorry. Just like No, I'm asking because
sorry for that.
No. It's okay because you are in ICT together, and then he has another system which we talking later. I mean, for the disaster monitoring. So that's different, but need a higher bandwidth, to do so. So if we could integrate this and into the system he already, has for that, I don't know, volcano, but we try to use it for the smoke detection in the remote area. So
we applied this protocol to the wide fields. One is at the agriculture, and one is at the disaster monitoring, and also the town monitoring.
Okay, like that. Okay, I can tell you here that we need to talk more later then.
Okay.
Yeah. Okay. Thank you very much. Wonderful. Okay. As Professor Rabi, any question from the floor? Any further question?
Yeah. Thank you, Chai. Thank you, Chai-san. Yeah. I can see very interesting one, as you said. My only question is, we always have problem in, transmitting the high density remotely censored data. For example, any spatial image, and if you want to do any image processing, can your system help Nagatsuma-san?
So what is the key of your question?
The question is, for example, if you want to do any analysis or even transmitting the training on using the remotely sensed data to the students, which is very high dense images, can we do it through your system?
Yeah, we currently we are transmitting real-time image data for HD quality, HD video transmission. We can enable to transfer by using our system.
Okay.
Yeah, Adi, that's what we trying to do.
Yeah, that's fine.
But
that's fine.
I don't know. He said that we need to get the system up because he have one system at the his student. Now he's a lecturer. Gogo was his name, and then with the Chalermpon from NECTEC, that they also have the system, and we have to test it to send the stream to Japan to NICT and check it out how well the system can do.
Thank you. Yeah. Thank you very much.
Yeah. Then we can share later if it's successful, because this is gonna be connected with the camera. I think the low cost camera first to transfer the stream of video to NICT for the analysis, because they have the cloud-based AI for the, I don't know, smoke movement or something like that in NICT.
Okay.
Yeah, actually, maybe the such kind of detection algorithm maybe explained by next speaker, Dr. Kikuta.
Oh, okay. Then we listen to him in the third speaker, because we bump up.
Right. That is the third speaker now.
Yeah, because okay. Then Dr. Qinyang agreed to move to the second session because he's the last speaker of this session. So now it's set. It's fine. Okay, Professor Rabi, you can start yours. Then Dr. Kikuta can follow Rabi, because Professor Rabi need to be somewhere physically in the meeting. So Dr. Kikuta, okay. Rabi, can you go to third? You already shared.
Yeah, I have my system is not permitting accessibility.
Okay, then you go third. Then it's still okay, right?
Yeah.
Okay. Dr. Kikuta, please continue.
Okay, I'll do. Yes. Okay. So I would like to talk about this tracking tapetum. So this is I think we use same kind of system with same kind of system with the previous Nagatsuma-san's presentation, but so now NICT is doing many monitoring application with visual IoT. So this basically the system is that we use monitoring camera, which is very common PTZ cameras, easily purchased, and we connect it to these cameras to Raspberry Pi, so that we can control like data acquisition interval, or how much the image videos are compressed, and we send these image videos via normally 4G networks to the server or the monitoring with receiving with Raspberry Pi. So now this time what we do is the tracking of eyes of animals. So it is there are many application for detecting the animal movements, and so many nocturnal animals have these tapetum in their eye, which glowing when exposed to infrared light. So if you observe these animals in infrared light, it is easy to detect eye movement. It's very bright in this image compared to this daytime cow image. So in this research, first we apply this tapetum detection to this dairy cow. So what we used is IR camera system, which can obtain full HD video with 85 frames per second. And so we conducted tapetum detection using visual characteristics of these and we use optical flow to detect tapetum. So optical flow is a method to detect movements in videos by comparing brightness of frames. Specifically, we use this Lucas-Canadian method, which first finds some very specific characteristic area, which is corner points of image, and only track these points. However, normally, simply I just think the conventional this cannot just track only tapetums because many corner points exist in these images. And this curve diary, so there are many cases and these kind of very significant edge characteristic exists. So, but we only want to see the movement of eyes. So we utilize these high reflection of the tapetums and extract only. We want to only extract areas of tapetum. So first we get this image from just make threshold of by brightness of image. So you can see that this point is tapetum, but however, in this case, so there are many other reflective parts, which is hay or the cages. So in this case, it doesn't work like that. So then we extract darker area of the image, which you can see that the silhouette of the curve is can be seen. So, and by combining these two threshold image, so we got this kind of images. So now the bottom image, which extracts the darker areas, have some, I think, voids inside the curve silhouette, but we filled these voids, and you can see that curve shape are more clearly shown, and you can see that in these curve areas there's a red. These red circles are the area of the high reflection, and you can see that there's tapetum exists, and only extract these area which both threshold criteria can be realized. Is this kind of only tapetum can be extracted. So now we simply decide this point as a tracking point, and we can apply the optical flow and track the movement of this tapetum. So, okay. So this is the result of optical flow tracking. So in the left image, you can see this here, the tracking point exists. And after a few seconds of videos, the cow moves, and you can see the track of the movement of this eye movement. So it shows this actual video. Okay. Okay. This is the movement. You can see that. eye movement can be tracked. Okay, and this next example, which in this video, the halfway of the video, the cow's head go outside of this frame and disappear, but we set the each frame we trying to find the tapetum when we say lost the area. So in this case, I go outside and then it will search for the tapetum after the area disappeared, so it can continuously monitor the movement of these areas. So for the application of this method, so if we think about in this cow situation, this cow is so pregnant, so we think it can be interesting that we compare the difference before and after the childbirth. So we obtain the pixel value of eye movement before and after childbirth, and plot how much. So this is the x-axis is the motion pixel value, and y-axis is the frequency. However, comparing before and after the childbirth, there's not so much difference appears. So in this case, then we find out that cow doesn't change behavior because of the pregnancy, I think. But however, so this is the kind of trial experiment of the tapetum movement using this closed situation. But our main purpose is kind of future studies, but we are now trying to detect the wildlife animals. So many wild animals are nocturnal, and so it is important to detect this wild animal movement like in field, so that prevent damage to kind of crops or like that. So now we are creating these monitoring system outside of these areas, and if we can detect these detect the movement of animals by tracking tapetums, we can we can do the sound alarm or other things to prevent animals getting inside these kind of areas. So now we are developing systems for these kind of wild animals. Thank you very much.
Okay, thank you very much. Wonderful, wonderful. Any questions from the floor? Okay, no, I have one question. Since you use the system to detect the wild animal, can it also give the signal that okay, it's coming, right? It's automatic giving you the signal that this animal is coming into the field, something like that, right?
So I think, this kind of method we can detect that some bright spot moving constantly, and then we can automatically detect the
send the alert to the farmer, something like that.
Yeah.
Okay, so then I think we can apply to the wild animal like elephant, something like that, because there's a system between a problem between elephant and people and horsemen, and the system can detect the eyes movement of the elephant coming into the area that the people living, and then can can, you know, give a warning to the people. So could be possible.
I think tapetum affects strongly for nocturnal animals, and we think about like boar or like that kind of animals. It's very common in Japan. So I think these can be separately detected because of this tapetum's reflection, I think.
Great. Okay. Great. Thank you. Oh, wow. Any question from?
Yes.
Ninomiya-san, please.
How are you, DJ? I have a very simple question. Just I wonder if every animal does have their tapetum in their eyes.
In this case, you can not detect, but I think nocturnal animals have tapetum, and we want to monitor the night. So I think
So in case of nocturnal animals, they have. Okay, I didn't know. Okay, thank you.
Okay, any further question? Okay, if not, thank you very much, Dr. Kikuta. Probably we'll have to talk more later after after APAN. Okay,
thank you.
Please, Professor Rabi, are you there? You are next. Are you there? Oh, he's gone. Oops.
This is Zhang. Can you hear me?
Yeah. We're gonna switch Professor Rami to the third, but he's gone. So
okay.
I think you go ahead because of the time. Please,
thank you.
Dr. Zhang, please.
Let me share my desktop.
Okay.
Can you see my display? Yeah, thank you. So this is Zhang from the University of Tokyo, a researcher from Field Phenomics Laboratory. And today I would like to briefly introduce our research about an open source AI platform for visualizing digital clone agriculture data in breeding experiment. So today's flow is like this. And firstly, I will introduce the background about digital clone and digital clone application in agriculture. So digital clone is a technology that involves deep learning, which allows one to manipulate current existing audio, photos, and videos that are hyper-realistic. One of the impacts of such technology is that hyper-realistic videos and photos makes it difficult to the human eye to distinguish which is real and which is fake. And here are some examples of digital clone products. And this first one is a digital Einstein that can communicate with people in a way that comes most naturally using conversation, human expressions, and emotional responses. And this one is a scientist from Japan. He demonstrated the digital clone of human values and expertise. And also, some company have started a service for generating one's own digital clone in metaverse. And these examples are all about human digital cloning. And now I would like to introduce a little about smart farming and why we need digital clone for agriculture. So in conventional farming, there are typical 3 steps. The first, farmers conduct observation in the field about the crop status. And environmental conditions such as weather, soil, water. And next, based on the observation, they make decision for their field management. And at last, they conduct the decision for the field management. So in conventional farming, the first step, observation, is done visually, which is inconvenient and subjective. And based on the observation, the decisions are made empirically. Finally, based on the decision, they conduct empirical operations, which are laborious and inefficient. For in smart farming, the observation in the field is by IoT sensors and images which are automatic and objective. The frequency of the observation can be very, very high. And finally, based on the decisions, the robot will operate accurately and labor costs must be much small. For smart farming, the most important fact is that it can understand the growth of plants automatically, which is called field phenomics. So for plant phenomics, the plant modeling is an important part of analysis. An accurate generated plant model can be regarded as a digital clone of the plant. And with the digital cloned big data, we can analyze and predict the growth of the plant. And today, I will talk about these two parts: the modeling and the visualizing of the AI platform. And in the next section, I will introduce some techniques for digital clone of crops and some approaches to visualize the data that we developed. So for some small individuals, we use rotating platform and single lens reflex camera. By taking 360 photo of the crops, we can accurately generate the 3D digital clone data of the plants. The photos above are the digital data. Here, the examples of the sweet potato, flower, and broccoli. And in greenhouse, with a similar method, by taking 360 photos and through frequent measurements, we can get the time series 3D data, and we call it 4D data, and know the growth of the crop. And in the field, for the large-scale measurement, we usually use drones and robots to complete the frequent data collection over large areas. And with high-resolution image data, we can also get large-scale digital clone data of the field, like this. And in the next section, I will introduce our AR visualization platform. So the AR platform consists of 3 parts. The first part is a 4D generating system with 3D models and time series data. And the second part is the AR glasses, which has an IMU sensor and an onboard camera. The third part is the application that's developed by 3D engine. We developed an open source platform based on Unity, and we use IMU data and onboard camera. We can detect the movement of user's head and get the movement of the user's hand to get the interaction. And the AR glasses we are using is a sunglass type AR glass, which is called Matrix Eric. And unlike some expensive AR glasses like HoloLens, this one has smaller size and lighter weight, also lower price. It also has 2 lenses, and users can see through of it like this. And we developed our 4D plan visualization application on it. So for next part, I will introduce the 4D representation of the real plants. To achieve the 4D data, we use the 3D construction system to record the time series data. The plant is put on the rotating platform, and its 360 photos are captured with several cameras. And the single color background and some random markers will help improve the accuracy of the modeling. And by recording plant every day, we can guide the time series digital data. We can see the growth of the soil. And this video shows how to use one hand to interact with the digital soil data. We trained a neural network for hand detection. And by detecting gestures and movement, we achieved some functions like dragging and rotating. For visualizing the growth of the crops, we can see the 3D model of each state. It becomes bigger. Can rotate it. And last, the summarize. So we use the 3D construction system to collect the 4D data and developed an AR visualization system. Although the interaction is still difficult and a long way to go to get a perfect interaction. And for the future work, we want to combine the real world and virtual data to get the realistic visualization. So yeah, that's all of my presentation. Thank you.
Thank you. Any questions from the floor? Okay, no. Okay, would you stop sharing so Professor Rabi can try to share his? And he can do is, I have one question. We mean like for the difficult work, long way to go. How long you think it's going to become reality?
Yeah, yes, thank you for your question. And so my purpose is to make the AR glasses to achieve the same function like HoloLens. So by the limitation of the sensors of these AR glasses, I think I still have to develop the hardware to get more sensors to sensing the hand, the depths of object, and so on. Also some functions like SLAM. And yeah, I think it's a long way to go, like 1 year or 2 years to get it.
That's not long at all. No, that's not long at all.
Thank you.
Yeah, okay, long I thought like decade.
Yeah.
So 1 or 2 years, not long at all. No, it's not. Okay.
Thank you.
Okay. Thank you very much. Any further question? Okay. No. Thank you very much. Thank you very much.
So much.
Would you stop sharing? Okay. Professor Rabi, would you start to share yours? Okay, it's coming. Oops. There, full screen, please.
Yeah.
Okay, thank you. Start.
Great. So very good morning to all of you, and sorry to encroach to some other time because of I have some preoccupation and I had some problem with my system. So I'm going to talk about sensing and data analytics for smart agriculture. What is the possible approach to enhance the productivity? That's where the question comes in, and how my previous speaker was talking about the plant phenomics using different techniques. So how we can design a very good smart crop that can be done through phenomics, and which can minimize the yield gap between the actual and potential yield. And other approaches, if at all, we can go for site-specific input management through the tools and techniques of precision agriculture. So that can optimize the production system. enhance the productivity. So there are two approaches to minimize the yield gap, whatever we have. So how tools and techniques can be helpful to us with respect to precision farming and phenomics, that's what going to be my talk. So in precision agriculture, the variability is the key issue to handle with, and those variability can be because of the inherent soil variability, maybe because of the management, maybe because of the environment. So how we can manage this variability using those sensors and data analytics, so that can help us optimizing the production system. And if you can see down there, the picture shows you how in a 4.4 hectare land, you have that kind of variability and which is reflected on the yield. If we can able to manage this variability, then my production system is going to be optimum. Again, those kind of attributes which you are going to vary in a spatial and temporal scale, that all depends how they vary with respect to space and time. And one has to be very careful to look at those clusters, how they are variable with respect to time and space, and accordingly we can go for management. So precision farming would be potential if at all there is a variability. If it is not, I don't think it is going to be potential is going to be useful. For example, conditions like India, conditions like developed countries where you have a large holdings. So coming back to tools and techniques, these are some of those approaches which can be used for precision agriculture. And you can see the challenge remains is how we can make it possible in near real time, and how we can use the communication innovations and service science very useful, because mobile network is well penetrated to the stakeholders, to the farming community. Again, challenge is how we can Indianize those technologies for the small farm holdings. So these are the challenges and issues, whatever we have, like developing countries or Asian countries like India. So the sensors which can be used in both optical, thermal, and microwave, there are already many developments has been occurred. And again, with respect to spectral channels, both panchromatic, multispectral, hyperspectral data, how you can use. So this is what our technological advancement. And with respect to platform, again, from the ground to airborne and satellite, how we can do. So coming back to the scalability, starting from a single pixel in the lab conditions, what you can observe and address some of those science questions, what you have for the soil or plant parameters. Same thing, same instrument you can take to the field. You can put an HAE picker, or you can put over the UAV and the drone, and finally on the satellite. So whatever the predictive model you are going to develop in the lab conditions, how you can go to the last field conditions with the satellite, this is what kind of uncertainty, a risk, whatever you have, how better we can develop those models. This is what the kind of approach one should have. So coming back to the ground sensors, these are some of those sensors which we have been using in the generating some of those spectral signatures which can characterize both soil and plant parameters. So this is a sensor in the lab conditions. This is a sensor which can be gone on the airborne. And these are sensors again in the lab conditions, create some of those signatures and can go for the predictive model for that purpose. This is the sensor, the plant phenomics center, where you can have the plant moving into different imaging platforms and capture the data using these kind of sensors who are listed over here. Or you can have a mobile platform where plant can be grown and sensor can move on a framework or on the drone or on a mobile platform like robotics, which you can integrate the sensors and fly with, and you can move in the field itself. So in case of coming back to the airborne, these are the drone sensors which have been used very popularly, very commonly. How we can use all these sensors for the phenotyping or plant parameter retrieval. That's what the predictive model data analytics we need to use for. For example, these are some of those birds which use those sensors and capture the data also on the ground using the mobile platform. And these are what data analytics tools and SOPs which has been developed, how drone-based plant phenotyping or plant parameter retrieval can be done with. So coming back to the satellite level, India has so many missions has been launched till now and so many sensors with respect to spectral, temporal, and radiometric resolution. The development has been taken place. So we have a lot of success stories with respect to launching and the data product which has been generated. Similar, also we have airborne remote sensing. Since 1969, we have been doing till now. We have many collaborative programs to develop sensors airborne capturing those data. For example, you can see the more than 50 years of the technological advancement what happened in the country. 1969, this is what the black and white image you get somewhere in the south part of the country. And now in 2019 and 2018, we have airborne campaign in the same plan, how better detailed information you can capture. So what I mean to say over here is what the technological advancement has been taken place, how wonderfully we can retrieve the information. So coming back to the airborne campaign, this is what the manned aerial vehicle, this is NASA sensor, which has been integrated on the flight, and we capture the data wonderfully. Same time also science campaign and retrieve those parameters. So some of those success stories I would like to these are the data analytics which has been used with the kind of data what we generated over the years or over the different sensors and try to retrieve some of those parameters. So some of those examples we have given is we develop those pipelines and methodology, how automatically you can retrieve some of those sensor-derived data and the parameters. So this is what the drone-based data analytics. Once you fly the drone, either in the control field experiment or the farmer's field, you'll be able to retrieve some of these parameters called chlorophyll, leaf area index, or other parameters, which can easily be used not only for phenotyping and also precision agriculture. So coming back to the soil retrieval of the parameter. So this is one of the study which we carried out with the ground truth and also airborne campaign. And you can see the kind of predictive model what we try to use from the airborne campaign and also from the lab studies. So you can see the some of those parameters which has been tried to retrieve. You can see the predictive model from the lab conditions, the R-square almost going more than 0.75. When you go to the airborne campaign, you can see also R-square is prediction is very good using some of those data analytics tools what we can do. The possibility of using these sensors and airborne for the soil health assessment is the hope now, and that's what the national level program we have for the soil health monitoring, and that's the possibility we can use UAVs for that purpose. This is one of the example. What you can see the airborne image, and the right hand side you can see the organic carbon mapping which has been generated using those predictive model and data analytics from the airborne average energy sensor. And coming back to the satellite, this is what the satellite long back story 2008 we did that kind of study somewhere again northwest part of the country, and you can see the lab conditions, field conditions again on the satellite level, how predictive model has gone down. But what I mean to say is still there is a hope if you can have the satellite data using the having the imaging spectrometer, that kind of predictive model in the regional scale soil parameter can be retrieved. There's a recent concept of digital soil mapping. Instead, in addition to imaging spectroscopy, you can use some of those multispectral data and also some of the environmental covariate using this in the long-standing equations, Jenny's equations, the soil formations, and retrieve all these parameter and put them together, and having the legacy data, you can retrieve the digitally soil parameter. And the benefit is that you can make a dynamic soil fertility map at every 6 months, 1 year, 2 year interval, and using this environmental covariate, which can be retrieved from satellite data products. For example, you can see here, these are those environmental covariates which has been retrieved using multispectral data, remote sensing data. And this is what the legacy data we have in the field, around 280 data points, and try to run through random forest modeling. And finally, we try to get this product generated. So these are some of those 17 plus soil parameters which has been generated using this digital soil mapping concept. And you can see the predictive model and the concordance, how wonderfully they are. So the possible use of this concept in the pan India is going to be very useful to complement some of the program what we have with the soil health. So if at all you develop the soil fertility, then what we can do is you can pull them together. This is what the different major nutrients, nitrogen, phosphorus, and potassium. This color says you low, medium, high. You pull them together, make a composite soil health map. And for each color, you have a target yield of rice, wheat, and maize. And these are what 8 color units you have. And accordingly, you can customize the nutrient applications. So this is what the precision agriculture you can do in a larger scale in the block or district level. And accordingly, so this is what the homogeneous unit you can generate using the sensor-derived soil fertility map, and using some of the modeling and target yield, you can go for the customized fertilizer doses for that purpose. Coming back to the drone, precision agriculture, plant phenotyping. This is what we call drone-based sensing. Is nothing but a CATS kind of for the purpose. So you can see the kind of the data which has been generated using hyperspectral and multispectral data, and at the different stages, and you can go for phenotyping different reels, recombinant inbreed lines from the parent and go for the matching of that purpose. So this is what the experiment what we have, and this is what the derived indices, derived the values, and you are trying to see how they are deviating from the parents, all those inbreed lines, and go for the matching, how best we can develop those varieties for that purpose. So since we say the sensor derived parameters are reflection of those attribute, if at all I can go simply for spectral matching using the hyperspectral data, then I don't need to go for all those biophysical parameter retrieval. Simply spectral matching with the parent, it will be telling us which reels are really good with respect to parent, and that's what the fast breeding or quick phenotyping can be done using the imaging spectrometers. So this is what the different sensors we try to use in the field to see how wonderfully you can, from the RGB to multispectral and hyperspectral, the predictive model can be better to retrieve some of those parameters which otherwise is not possible. So this is what the one example what I would like to say. So from the airborne, this is what the variable treatment given in the field, and this is what the leaf nitrogen level you are able to get. This is what the prediction you are getting from the UAV imaging spectrometers using some of those data analytics tools. So this is what the possibility of getting this variable map generated. And similar studies also we try to do using the imaging spectrometer. For example, you can see here, this is what the raw data, and this is what the nitrogen content map of the field, not only from one field to other field, also within the field, that kind of variability you are able to get. So this variability you are able to capture. This is what the thematic map you are able to generate. Next will be the management map to see how best we can manage using mobile platform, or from the drone you can go for liquid nitrogen spraying. So this is what the kind of all possibilities you can do. Similarly, using thermal sensors, you can go for the irrigation scheduling, the plant canopy moisture deficit mapping, or generating heat map, which part of the plant or which genotype is really doing good or bad. Similar, this is the biomass predictions using simply low-cost RGB sensors one can do before harvesting. So these are some of those tools. And coming back to the biotic space, some of those hopes, tries what we try to do. If at all we can detect BPH, rice brown plant heifer, this is one of the major pests. And if we can detect by the spectrometers, this is what the disease called yellow rust disease in case of wheat. We can do by the sensor. If at all we can generate those. Again, this is a rice blast, which is again one of the important disease in case of rice. We try to use the sensors, how best we can detect them. And these are some of those data analytics tools to phenotyping purpose and retrieve those parameters. For example, the number of years and counting them using the yellow technique of CNN, and also the tassel counting using the RGB images. So these are some of those data analysis technique which we try to use. Again, try to use the Google Earth Engine to real-time monitoring of the systems using the Sentinel, European satellite data, and real-time if you can do the crop condition monitoring. This is one example what we do in the 2 seasons of rainy and the winter season of the farm. You can do the crop health index mapping. So the conclusion would be, so what you need to have is at all, if you go in a larger scale, you need a good spatial extent of pest and disease to be monitored. And you need to develop the tools and techniques to differentiate the composite stresses, what you get in the field conditions, and also severity level assessment, and how best we can, sensor best we can quantify the economic threshold level so that you can go for the management options. Again, sensor based early detections. Again, low-cost sensing technology is the need of the hour, and how mobile platform can be used, both robots and UAV. And again, data analytics, genetic model, and making it more real-time input management options. And again, if at all we can use those mobile technology for all these innovations to transfer to the stakeholders. So keeping that in view, this is what a bigger program we have taken in the country scale, aspecting soil, crop health, decision support system, BIT, and we have number of centers who are working, including precision dairy and fishery also. So thank you very much for the giving this opportunity to share some of this experience, what we have, and working with a team. And thanks to each and everyone who have contributed those kind of studies. My students, research fellows, Professor Adi is here, who is a very good collaborator with me, and fellow colleagues who is associated with me. Thank you very much.
Oh, yeah, thank you very much. Very informative, very advanced to show that what India is doing. So any questions from the floor?
Oh, yes, I have a question. Can I?
Please, please.
Oh, someone just, yeah, can I? Okay, thank you very much, Rabi. It's really informative. And I don't have the particular question, but for example, you show me a slide with a table with R square between the soil parameters and hyperspectral estimation. Would you go back to the slide? I don't see the number of the slide.
Yeah, I have unshared the screen. You want me to stay?
Yeah, okay, doesn't matter. But so have you published the data? Just I'd like to know, about the data.
We are in the process of publishing that data. Just we finished that data in one of the PhD student. So we are
okay. So which journal should I check for the publications? Actually, you have published several papers.
I think once I'll be sending to Geoderma, and once I get the confirmation, I'll set the paper itself.
Okay. Thank you.
Okay.
Okay. So Jaime, please.
Yes, Rabi, nice presentation. I have two questions. Number one is, are you using ArcGIS or are you using QGIS for your work?
For that work, which I was showing different color maps, compositing them, developing homogeneous unit, we use ArcGIS in that case. So we have not used QGIS. We have used.
You have not used. So you have no experience in using QGIS.
No, we have experience. We have my students are working on QGIS, but that work which I showed that we use ArcGIS.
Okay. Now the second question is the mobile decision support. So when you actually you are simplifying the whatever that you found in ArcGIS and then transfer it simply so that it can be displayed in mobile format or maybe web-based format. Have you done that?
Yes. So some of those data what we retrieve from the drone, the platform, finally you do image processing, or finally the thematic product you can put in the ArcGIS environment, and same map can be put into the sensor for the variable rate applicators. So behind it is a special data, and you can use ArcGIS for that purpose, but we have not done yet for the application purpose.
Okay. And then and for the decision support using mobile, have you considered, because we are in this same game together also with RISE, and it's one of my projects. The challenge is actually to put it simply so that the farmers can see it in the mobile, and then give them a warning saying that, hey, your plant is in the brink of getting a leaf hopper or some sort of things. And then we use Telegram bot to actually telling them back, you have to back up or you have to do your spraying and so on and so forth. So that is the thing that at the brink of what we are doing as far as
wonderful framing. Support. I think this is what my dream for my network program. And we are able to see if at all we can get all those data on the server and mobile connected, and the farmer is standing in the field and he has the geolocations, he'll be able to get the crop conditions, and he will get the decision again from the server, my server. So we are going to use the geo server for that purpose and answer those questions. That's what my dream, and we are working on that aspect.
Okay, I think we have to we can talk. Thank you.
Yeah, so nice of you. Thank you.
Okay.
Thank you. One more question from Professor Wang from University of Tokyo. The question is like, how do you handle the data across the different platforms? That's so many. You so many.
Sure. So this is what the question at the end. I was putting one summary. This is what so you have the data, as I was saying, You have the data in the lab conditions, you have the data from the airborne and manned aerial vehicle and also satellite. So irrespective of the platform, the sensor, the physics remains same. The interaction is going to be same. Only the condition is going to be different. So whatever the prediction model we develop in the lab conditions, when you go to the field conditions, when you go to the airborne or satellite, the prediction model may change. But the principle remains same, but the sensitive bands will remain same. So purpose of doing that inter-platform calibration or evaluation is we need to answer some of those science questions in the lab conditions, some of those solutions. And when you do go for the field conditions, same model cannot be used. So there will be different model for the field conditions to help the farming community for the soil or crop health. So that is the purpose. We are using different platforms. And when you want to have the soil samples in the lab conditions, so in the lab condition, easily that prediction model getting better prediction equations, ask a value, so you can do that. But when you go to the field conditions, that prediction model is going to be altogether different because of heterogeneity, light conditions, many other factors, noises, what you have in the surface. So that's the reason we have different models for different platform and conditions why we have used for. Thank you.
Okay.
All right. Thank you very much.
Okay. Any further question? Okay. Not. I have. Well, the time is running, but I need to ask because you use SAR. I saw you use ALOS from Japan. How well ALOS or Sentinel-1 that can get the soil's moisture product out of those SAR data? How well you can get, because the Japanese side, I mean, like from Restec or JAXA, said not very well.
So you mean to say SAR data, you don't get good soil moisture data?
Yeah, the thing about the product, when you get the soil moisture, that product from the SAR, such as ALOS, ALOS2, not well. That's what I heard from the JAXA and Restec themselves, like really.
Okay. So the possible reason for the SAR synthetic aperture radar for the soil moisture is the noise, the roughness factor, which is a challenging factor for minimizing, scatterometer. Again, which band, which frequency you are going to use. And again, the resolution is the challenge. So here we have optical data, but same time, what we are trying to do is the soil forming informations, like from the Jennings equations, what I have told, those environmental covariates we are able to derive from multispectral data. And we have a legacy data on the ground itself, which has been done by wet chemistry. Try to match with them and evaluate them and develop the prediction model using some of those data analytics like random forest we have used here. You can use any other to see how better we can derive. So this is what the digital soil concept. I think in many European countries and US, people have started working on this, many success stories. And we try to see in that farmland, what we have around 5 hectare land, we try to do that. And also in different part of the country, we're trying to do it. So this is the reason why we get better results, because we take care of all those parameters by which those variables can be changed or predicted.
Okay, thank you. Please, one request from other. We need to take the photo before the Professor Rabi leaving. So please turn on the camera so we can capture. Huh! Suhaimi, you are here. You're still here. Yeah.
So nice to see everyone.
Yes, please turn on your camera.
My friend Adi is there, and you know me as well.
Yeah. Oh, the light, Abdul, the light behind you, that's why. Okay. And then, Hattori is here too. Hattori, would you please turn on your camera? Yeah, thank you. Okay. Okay, 1, 2, 3. Thank you. Got it, Titipon, you got it too, right? Okay. All right. Okay. Thank you very much for your wonderful and informative talks. Okay, then the next speaker, well, we run out of time, but don't worry. The next speaker is Wang from Dr. Huasong from University of Tokyo. Please share your slide, please.
Okay, I will share my slides.
So is that everyone can see my screen?
Yes.
Okay, so I will start my presentation. Good morning. It's glad to have a chance to share my recent progress on the procedural geometric modeling for the plant phenomics by Blender. We're using a Maize as a case study. So in this study, I will introduce the background first. As mentioned by other presentations before, the digital clone is very important that has a bright future for the agricultural applications, especially it can manage the operation remotely based on the digital information. Also, it can simulate the operation effects and find the best operation immediately. However, in order to apply the digital clone for the plants, we need a plant 3D model which is a fundamental for realize the digital clone. And currently, there are several different types for the 3D plant models, mainly about the three main types. One is a point cloud, which is a group of XYZ points to describe the shape. And the other is a voxel model. It's using a matrix that's similar like a raster image to describe the shape of the plants. And other thing is the mesh model, which is using the record the edge and the vertex points to describe the model. And for three different types have different characteristics. Firstly, for the point cloud is mostly used, but the point cloud is disorderless. So it's hard to analyze the point cloud easily. And for the voxel model, it's easy to analyze because it's similar as a common image, but it's often have a low quality to get the such model. And the mesh model is preferred, but to convert the point cloud to the mesh model is a challenging work, based on current algorithms to get a perfect transform. And currently, there are two main methods to obtain the 3D models as mentioned before. The first one is modeling, which is create the non-existent plant model from the shape and structure simulation. I will introduce the manual modeling and the procedural modeling later. And for the second method is called reconstruction. It's building models from the existing plants by photos or 3D scanning devices, mainly about the laser-based scanning and also the image-based reconstruction. So first, about the modeling. The modeling, especially the manual modeling, is the most common way to get the plant models. The performance is highly relates on the modeler who takes control to building the model by his hand. And the commercial models are also available on some website as mentioned in these notes. And the price is around the $10 per each for the model. And for the manual modeling, it's currently suitable for the CG or game industry as an asset for this industry. As it's not a good choice for agricultural purposes because it is very expensive to get each model for each variations for each plant in the field. So some researchers trying to using some parameters to control the shape of model instead of manually modeling. One trail is by the L system. It's using the string iteration to draw figures as mentioned in these examples. It's using several strings to describe the shape of each plant, and it can draw 3D or 2D images or 3D models. And here is an example to show how the procedural modeling can do to get the 3D model for the actual images. And we can see by adjusting the parameters here, it can change the model shape to fit with the actual model by this research. And the other way is called the commercial software, doing the similar thing as the L system, but it's using some commercial software for modeling. For example, it's the Sigma 4D or Houdini. It can using parameters to control the buildings or arts shape like this. And it is also possible to get the similar thing for the plants. This is the 3D modeling, procedural modeling made by Blender. and the growth images, growth plants like this by controlling the growth parameters. And the other way is called reconstruction. It instead compared with the building from the non-existent plants, virtual plants. This is mainly based on scanning or taking photos for the existing plants to get the shape. And for the laser scanning, it can using devices by the laser to calculate the distance from the object to the sensor to get the 3D shape of the plants. This method is accurate, but the laser scanning device is not very price friendly. And a much cheaper method is called the image-based reconstruction by using some devices taking photos, and the software will calculate the photo relationship between each other to get the 3D models. And this is a model that we can build for the sweet potato in this platform. And this is cheap, but we, as mentioned in this picture, we need a very good quality control for the images to get a good plant model. And the question is, can we combine the beneficials for both methods together to get the final results, which is for the modeling, it is flexible, but not so real. The plant is not real. And the reconstruction is real, but it's not flexible. Will it possible to combine them together to get a flexible and adjustable real plants? The answer is by our studies. Firstly, we're using the 3D reconstruction platform to get a real maize plants. And this is the devices we use to get the 3D plants. And we also get some batch scripts to make this processing automatically. And here is the time series data that we get from our maize. And then, inspired by these two studies, for the whole maize can be splitted by a phytomer, which is consisted by an internode and one leaf to describe each units of the maize plants. And then for the leaves, it can be described by 3 curves. One is the middle rib and 2 of the edges. By using these 2 published papers and their ideas, we combine these ideas with our Blender applications. We're using the Blender geometry nodes graph to facilitate the previous ideas. So here is the maize phytomer that we can build from in the Blender, consisted by a stem and a leaf. And here the video to show, here the video to show how we can facilitate with our field scan data. Here is the models, final data models that fit with the point cloud. And we can see here is the model we get by our technologies. And this is the edges, the mid rib and the 2 bounding edges to describe the model from the point cloud. By using this, we can get the very realistic model. And here is a similar thing. And we combine the whole maize by detecting the mid rib and the edges, and also with some scripts to describing this procedure automatically. We can get the canopy maize by our model like this. And for each model internode of the plants, we can adjust the root position, the stem length, the radius of the upper and the right down, and also the leaf angles for each maize. By using this technology, so we can adjust the model to fit any other different conditions for all plots. Yes, and that's all for my current achievement. And here's a short summary for my study workflow. Firstly, we use a room structure formation platform to get a real 3D models. And then we can using some automatic algorithms to get the segmentation for each parts, and also some detection algorithm to get the leaf internode and the edges. And after that, we combine the photos and with our models to get almost a realistic plant texture for virtual plants. And then for some simulations for further applications. And this is the part I described in this presentation. And this is my future work to need automation for this progress. And this also others I need some future studies to make this workflow become complete. And that's all. And welcome for questions.
Okay, thank you very much. Very exciting work. Wow, looking forward to. Any questions from the floor? Yes, Professor Adi, please.
Yes, Jai-san, I second you. I think it's a very wonderful work by this group doing Wang-san. A small question. We always face problem in getting the real leaf area index from the satellite or airborne images. That's because you see only from the top of the canopy, right? So whereas if you see the leaves below the canopy, right, that we are not able to get from the aerial platform unless we use some angles, right? If you take the picture from different angles, you can probably get the real leaf area index. Do you think this what we are doing it with tail systems or whatever it is, this virtual plant can help us in giving the real leaf area index, taking not only top of the canopy, even the below canopy also?
Oh, let me describe your questions. Do you mean in the field applications, it's hard to get the leaf area angles from below canopies? So will my studies can help to do this work? The answer is yes. And by getting the full models like this, we can get in the top characteristic of each plants, and then we can analyze the top angles for the virtual canopy. And after that, we can train a model that we only using the top parts, which is visible, to guess the below parts, which is not visible. We can train a model between the top part and the below parts, and then apply to the real canopies. We can measure the top parts easily from the UAV and using our trained model to guess the below parts. And this is a good resource to calculate the leaf area or leaf angles or leaf area index by our virtual model from the visible parts.
Oh, thank you very much.
Thank you.
Thank you. Then wow, wonderful. Then we gonna have a better biomass estimate than what we have now. Okay, that will be great.
Thank you.
Okay. Okay. Thank you. Will you stop sharing? So the next speaker, Dr. Tang Li, please share your screen. And this is the last speaker for this session. Okay. Please, the floor is yours.
Okay, thank you. I will share my screen. And can you see my screen?
Yes.
Okay, so wait a minute. Sorry. Sorry, wait a minute. I will share again.
Yeah, please share again.
Okay. So good morning, everyone. So my name is Tang Li from the Laboratory of Field Phenomics from the University of Tokyo. And today I'm very glad to share our data farmbot, which is a fully automated system for agriculture big data collection. And okay, so today's presentation will be divided into 4 parts. So due to the time limitation today, I will first introduce the background briefly and then introduce the native farmbots also briefly. And next, I will introduce 2 versions of the data farmbot we built based on these farmbots, and finally give our conclusion. So first is the background part. So as we all know, in recent years, the deep learning technology is developing very fast. So many more and more researchers are trying to apply the deep learning technologies to the agriculture domain. And but however, the deep learning technology is also a technology that requires a large amount of labeled data. So in order to train a better network, we also need larger amount of or larger scale of labeled data to support the large scale of parameters in the network. So, and also in agriculture domain, it is often not easy to collect those kind of labeled data because, for example, in agriculture domain, we need to go to the fields and take pictures or images, and also because in many cases the crops and the plants and the weeds are mixed together, so that it is also very difficult for the researchers to label those kind of mixed data. So we found these farmbot to realize the big scale, the big data collection to collect data automatically and remotely, and also to cultivate the plants remotely and also automatically. So basically, the farmbot is an open source CNC robot system with 3 axes, the x-axis, y-axis, and z-axis. And at the end point of the z-axis, there is a universal tool-mount system mounted to the end point of the z-axis, and we can mount different tools to the universal tool-mount system, like we can mount a seeder, which uses air pump to suck the seeds from the seed tree and to do the seedling job. And also there is a weeder that we can use it to destroy the weeds in the farmbot car. And also there is a soil sensor that can be used to monitor the soil moisture situation, and also the watering nozzle that can be used to water the plants. And also by default, there is a very small USB camera that is also mounted to the end of the z-axis, so that we can capture some more resolution images using this simple USB camera as well. Okay, so next, this figure here shows the very high level overview of the native farmbot. So basically, farmbot consists of 4 parts, and the top level here is the farmbot web app, which is a user interface that interacts with users directly, and so that users can do some programming. Also, users can capture some photos using the camera mounted to the UTM, and also can control the farmbot to move. And below the farmbot web app, there is an MQTT server that is a server actually located in America, and this is used for receive the command from the farmbot web app and then send this command to the Raspberry Pi, that is a Raspberry Pi located very next to the farmbot. And the Raspberry Pi here is running a farmbot OS system, which is also an open source system developed by the farmbot company. And after that, the farmbot OS will translate those high-level commands into very simple E code and F codes to the farmbot Arduino firmware to control the farmbot. Okay. So, however, the farmbot OS also actually has some problems. So first, the farmbot OS only supports plug and play cameras. So it is not possible to install additional cameras drivers to the farmbot OS. And also, although the farmbot OS is a Linux-powered Raspberry Pi, it does not allow end users to add and remove the software components running on the machine. So the official team from the farmbot also give some solutions, like to using the farmbot Pi or farmbot GS API to communicate with this MQTT server, or use another serial line to connect the farmbot with the sidecar to control it. And also there are two other solutions. Both these solutions, all these solutions uses a sidecar, which is actually another Raspberry Pi or another microcomputer. So in our study, we continue and we based on this farmbot and developed two versions of data farmbots to realize the data collection job. So actually, this figure in the back is the first version of our data farmbots. So it's built in a small greenhouse located in the University of Tokyo, and we used a sidecar, which is actually a NVIDIA Jetson here, and also we used 3 ELP cameras, and we mounted these cameras to the end of the Z-axis and connect these cameras to the NVIDIA Jetson, and so that we can collect image data. And this figure here is the second version of our data farmboard. So it's still underdeveloped. So this is farmboard also located in the plant factory located in the University of Tokyo. And in this version of farmboard, we will not use the NVIDIA Jetson, but directly use the Raspberry Pi to control the farmboard. So here is the first version of the data farm, and the right bottom figure here shows the example of the plants we grew in the farmboards. And okay, so next I will introduce our pipeline of the first version of the data farm. So here is the pipeline, and actually the key component in this flowchart is the NVIDIA Jetson, the sidecar, so that the NVIDIA Jetson can monitor the farmbot web app in a real time, and also send control signals to control the farmbot to give a sequence scan of all the plants. And also, at the same time, the NVIDIA Jetson will also send control signals to the cameras to collect RGB image data. And after the data are collected, there is also a Google Cloud Server that is used to sync between the NVIDIA Jetson and the personal computer. So because the Jetson here is used to communicate with the MQTT server via the farmbot Pi to control the farmbot. So it has some advantages, like the farmbot Pi API actually provides a very advanced interface with so that we can use a simpler control implementation to realize this data collection system. However, this workflow also has some disadvantages. So the most big problem we met during the actually data collection process is that this pipeline relies on a very stable internet connection. So because all the commands are sent to the MQTT server located in America, so that if we do not have a stable internet connection, the data collection will be interrupted. So, and next I will share details of our pipeline. So for remote control of the NVIDIA JetSong, we provide two ways to control it. So the first is the SSH connection from the terminal, and also you can also access to the GUI system using the VNC remote control. And both these two ways can be connected from the one using the reverse SSH tunnel, which is actually set up by using the Google Cloud server. And for remote data synchronization, we are now using the rsync program to sync between the Google Cloud server and the NVIDIA JetSong. And also, it is possible to directly mount the farmbot, the NVIDIA JetSong, directly to the machine, to any machine using the SSH-FS protocol. So here is an example that I mounted to the actually Windows 11 here. So it is very convenient to directly check the collected data. And for the camera control, we are now using 3 ELP 13 MP USB cameras. And the supported formats are listed here. And we are now using the GStreamer pipeline plus the OpenCV to control, to configure these cameras and to capture the desired images. And this video here shows the actual operation of our pipeline. So basically, the NVIDIA JetSong will control this z-axis to every position of the plants to capture image data. And here is the user interface, which is the farmbot web app introduced before, that can also be used to monitor the process. And here is the SS connection to the NVIDIA JetSong. Okay, so consider that we grow N species of plants, and for each species there are N plants of individuals, and we now have 3 cameras with 3 different angles, and we run 10 runs per day. So from actually from 8 morning to 6 in the afternoon, so that we will have about 300 runs per month. So in total, we will get about 900 multiplied by squared n images per month, images, fully automatic and fully remotely. So, but there also comes the very, very important, very, very big problem is that this system relies on very, very stable internet environment. So in the second version of the data farmbot, we replaced the farmbot OS with a regular Raspberry Pi distro distribution. So, and we also tried some other things, like we no longer use the wood car, but replaced by aluminum slice to build the cards. And also we no longer use the soil cultivation, but use the hydroponics. And also this time is a larger scale farmbot and grow more plants. And so here is the hardware design of our second version of farmbot. So Actually, we use the very same firmware as the farmbot before, but we use a brand new controller. So this is actually the program designed by Python to directly control to send the G codes to the farmbot serial and also receive logs and process the logs. And here is this video here, or it's not playing. Oh. Okay, I'm not sure why I can't play this video. So actually this video here shows a very simple example of how our new controller can control the farmbot. And also for the second version, we also developed a brand new user interface. So here is the image capture of our user interface so that we can realize basic controls through this user interface. And also there is also a built-in terminal in this user interface. So this is actually convenient for programmers to directly control the farmbot. And the left top figure here shows the VNC control of the Raspberry Pi system. And so finally, I will give our conclusions and also the future works. So in this study, we proposed a data farmbot, which is a robot system modified from the commercial production farmbot to achieve the automatic plant cultivation and data collection goal for building the agriculture big data efficiency. And the first version of data farmbot relies more on the native farmbots, but has the disadvantage of relying on very stable internet connection. But the second version of data farmbot developed a brand new operating system based on the native farmbot firmware, making the farmbot's operation not dependent on the stable internet connection. And for future works, so we will first further improve the convenience of the operation. So actually to improve the convenience of the user interface as shown before. And the second is to improve the efficiency of the data transmission. So we actually plan to use some NAS to directly synchronize the data between different devices. And third is to further reduce the cost. So now we are using the commercial farmbot, so the cost is relatively high. So in the future plan, we plan to replace the farmbot itself with very simple arms and motors. And the last one is in the future, we are planning to improve and also realize the fully automated, more automated cultivation system. And that's all. Thank you.
Okay, thank you very much. Any questions from the floor? Okay, wow, good. I mean, yeah, no question. So we will have a break, but before the break, we will be back in 15 minutes. But thank you very much, Tang Sang. And then we will join in 15 minutes. Oh, okay. For RD, he will join later, but it's okay. It's just like we will join, keep the same schedule. So Professor Jaywant will start first, and then Professor Qinyang will replace Professor Rabi slot. So we keep the same schedule. So see you a bit in the have a break now, like 14 minutes now. I think. Yeah, see you a bit. Thank you very much. Professor Jaywant, are you there? You can try to share your screen. You can try to share your screen so we.
Yeah, sure. Is it visible?
Yes, yes. Just leave it like that. So then wait for people to come back. 1 more minute.
Sure, sure.
Yeah, yeah. 1 more minute. Application to agriculture. So I don't know everybody here or not, but don't forget to send in your PowerPoint. If any slides that you need not to show on the website and the APAN 54 website, then you can remove that slide out. But please send in the slide you present so it can be posted in APAN 54 website.
Okay, I'll do that.
Okay, maybe. Okay, 1 minute passed. Would you kindly start, Professor Jaywant?
Yeah. Yeah. Good morning to all of you. Thank you. First of all, I would like to thank the organizers for inviting me to participate and give a talk here. In particular, Prof. Narayan was the one who initiated me to this group, and I've been interacting with Dr. Sumi or Sami. I don't know if the pronunciation is correct. So what I'll be talking about today is some work done by my PhD student Navneet Kumar, who is in IIT Jammu right now. And I also want to acknowledge the funding from Robert Bosch Center for Cyber Physical Systems from our institute and NASF ICAR. So I'll just describe some detail the experiments we've been doing in the lab, trying to understand heat and moisture loss from leaves and soils. So my background is mostly heat transfer and fluid mechanics, and not so, but we've been interacting with plant biologists over the past several years. So this is what I will quickly go through: basics of evaporation, transpiration, etc. Then conventional media, meaning like soils, but evaporation from non-conventional porous media, I'll describe very briefly what we have done. But in particular, leaf can be also considered to be a non-conventional porous media. And so we've done some experiments where we've developed a leaf mimic, trying to understand how the transpiration occurs from leaves. And also we've developed a new method to measure moisture loss in a very rapid way, but I don't know whether I'll just briefly allude to that. It's still work in progress. And all of us know that evaporation is a very important parameter in the whole cycle of water. And typically the evaporation rates are given in terms of millimeters per day. And so it can, so typically it will be like 5-6 mm per day. But of course, during the peak time, it can go to very high values. And of course, during the daytime, it will be higher, and during the nighttime, it will be lower. So, but it's important to understand what the evaporation rate is, both from modeling perspective as well as from agriculture viewpoint to for irrigation scheduling. And transpiration and evaporation are related to, in very complicated ways, to the light, air, and leaf temperatures, the airflow, and in particular that how turbulent the flow is or the wind is. And so it is a very complicated process, and some correlations are generally used to come up with estimates like the Penman-Montet equation, etc. Of course, as regarding leaves is concerned, it's much more complicated because of the stomata which keep opening and closing. But the basic physics is that you have some incoming radiation, And if you look at the energy budget, some of that radiation will be convected, some of it will be reflected, some of it will be lost as latent heat, and some of it will be re-radiated back. And if we are talking about a soil, then it can be conducted into the soil as well. And so this is a basic energy budget, but it's quite complicated in the sense how these various components interact with each other. And in particular, if you look at evaporation from a surface, if it's a dry surface, then the surface temperature is determined by the solar radiation intensity, wind, surface properties, etc. But if you look at a wet surface, like say a lake, then it's much more complicated. And in fact, the reason is because of the coupling between temperature and evaporation. So if you do some simple analysis, if you consider a very dark surface and assume some radiation of 800 watts, then it reaches a temperature of about 80 degrees. And if you look at dry soil, it's about 76 or whatever. And whereas water, the temperature for the same radiation will be much lower. And that is because of this large loss of heat due to the latent heat of evaporation. So it depends on all the optical properties, as well as finally the surface temperature is determined by interaction of these various components, as I mentioned. And so this is experimental data we obtained from different experiments. And this is just to show some overall view. So this is the incoming radiation, and this is the temperature difference between the surface and the ambient. And these are different surfaces like water, soil-like surface, plates, etc. So when the radiation is low, then all of them are sort of similar. The temperature difference is around 10 degrees, and you get a corresponding to about 400 watts per meter squared. But at higher temperature differences, then there is a difference between the leaf and the other surfaces. And this is a basic method by which evaporation occurs. Basically, it is evaporative loss is proportional to the concentration of water vapor at the surface and the ambient. And the concentration of water vapor at the surface is determined by the surface temperature, which in turn depends on the other factors. And of course, the rate at which this loss of heat and moisture occurs depends on the heat transfer coefficient or mass loss coefficient, which depends on the wind conditions, etc. But the point is that there is a strong coupling between temperature and surface concentration of vapor. And as I mentioned earlier, large amount of the heat is lost due to latent heat. So that makes a big difference between a moist surface and a dry surface. So we conducted, trying to understand the physics of this moisture loss from soils. We did several experiments, simple experiments, but we used different diagnostic tools to understand what is exactly happening. So the experiment is very simple. You have glass spheres or some spherical objects which are saturated with water. It is subject to IR heating. Then we look at the surface temperature using a thermal camera. And also we use fluorescein dye to understand how the moisture is lost and where the final deposition occurs. So this is important, for example, if you want to look at what happens to water-soluble fertilizers in the soil, etc. And so if you measure the evaporation rate versus time, then what we see is basically it is very high evaporation rate for quite some time. For example, in this case, it's for 30 hours, and then there's a sudden drop. So this is quite well known, but we were trying to understand what causes this behavior. And so if you were to look at when the evaporation rate drops compared to the average depth of the water, we see that as you increase the or reduce the size of the sphere or the particles, it goes to a larger depth. For example, for 0.7 mm glass beads, you get a depth of about 50 mm of water before this drop occurs. And we were able to find a relationship between what we call this capillary length at which this drop occurs compared to the bead size or the soil. And we were able to develop some non-dimensional methodology to find out when that happens for different fluids like water, pentane, and you get a single curve to determine when this sudden drop in evaporation rate occurs. And the result of that is shown here, for example. So if you consider something like clay, then the L cap or the capillary length is of the order of meters. Whereas for something like silt, it depending on the size, it keeps going down. So finally for sand, it is like a few tens of centimeters. So the point is that you have very high evaporation rates for a long time, even though the water level will be much below the surface. And we try to further understand what is the relationship between the surface temperature and the evaporation rate. So what is plotted here is the evaporation rate, that is this curve. So it's of the order of 20 mm per second, 20 mm per day initially, and then it drops down, as I mentioned earlier. And simultaneously, we looked at the IR images for this particular experiment. So when the evaporation rate is high, the surface temperature is low. It's low in the sense it's of the order of 40 degrees. And this is how the surface temperature looks like. So with time, you can see that these low surface temperature patches reduce in size, and then you start getting these high temperature patches. But the evaporation rate is still maintained high. And once it goes below, then the surface temperature increases by a large amount. So it goes to around 60 degrees. So the point why you get these high evaporation rates in spite of the fact that the water level is so low is because you have these films of water at this top surface, which allows this high evaporation rate to occur. And this fluorescein dye experiment was very interesting because, so I'm coming from a fluid mechanics background and we use fluorescein dye for flow visualization. So we thought we'll use this for imaging what happens in the soil as well. So, and it gave very insightful information. So initially, the fluorescein dye is kept in the saturated porous medium, and so it's green in color. And then at the end of the experiment, we see this pattern essentially. So what has happened is you get these brown brown deposits or orange deposits, which indicates that the fluorescein dye has deposited in these layers. And then you have this white portion where it's completely drained of water, and this green one which is still untouched. So basically all the water which was in this region has evaporated out, but this deposition of this fluorescein dye is something which was quite new for us, and it has to do with the evaporation mechanics near the topsoil. near the top surface. So this is, I believe, a nice method to look at movement of water-soluble stuff in soils. And we did other experiments, as I mentioned, using other types of porous media like plates and rods. And then also, if you look at a leaf, it has very some unique characteristics. That is, stomata covers only about 5% of the area, but we get very large evaporation rates, even though only small amount of area is open. So we were trying to understand this basic mechanism. So we made a leaf mimic in which we use silicon wafers and had small micron-sized holes to mimic the stomata. So I won't. This also turned out to be very interesting. The rods-based porous media, but I won't get into that now. But as I mentioned, even though the area covered is 5% in the case of leaves, stomata, about 50% of evaporation occurs if you compare it with the bare surface. And so this is the silicon wafer leaf mimic. And so again, some simple experiments were done with putting this leaf mimic on the surface and subjecting it to infrared heating as above, as I described earlier. And we measured in comparison with the perforation diameter of the holes, what the evaporation rate looks like, and tried to compare it with some known correlations. The main point is that you get these very high evaporation rates because the surface is heated, and that surface heating increases the concentration of water near the surface, which in turn increases the evaporation rate. So this coupling between temperature and surface concentration is what explains this very high evaporation rate we get in leaf-like surfaces. And anyway, so we looked at the budget of the different components. So the main point again, which came out, is that about 50% of the heat is going into latent heat. Rest is radiation and convection. So this has important applications in trying to get IR images of leaves and trying to understand what is the water stress. So we also have developed some quick methods of measurement of moisture loss, which is very different from the classical ones. So, but I won't get into this here, the lack of time. And so, yeah, so this is what that evapometer is essentially. And so finally, I will just quickly talk about some IR measurements of leaves which we have done. And so what we notice is that supposing the leaf is under light and shade, there's a huge difference in temperature across the leaf surface itself. So what that means in terms of transpiration, etc., is something to be studied, I suppose. But the point is that if we finally want to use IR imaging to find out water stress in plants, then we have to take care of these different effects. For example, here it shows the surface temperature, and also we used some reference surfaces to find out what how to interpret these IR images of leaves. So this I already mentioned, right in the beginning, that the evaporation rate depends crucially on surface temperature, but the surface temperature itself depends on other factors. And so for low temperature differences, all the surfaces, including leaves, are sort of similar. But at higher temperatures, there is a difference between the two. And we've been doing other work. I'll just quickly tell you. We've developed a new type of polyhouse for Indian conditions, which uses a solar chimney to enhance the ventilation rate. Then developed a standalone polyhouse, leaf mimic, as I mentioned, and also imaging system for growth monitoring, and some development of LED lighting for aeroponic systems. These are some of the references which I talked about in the talk. And with that, I will stop here and thank you very much.
Okay, thank you very much, Professor Jaywant. Anybody has any question from the floor? Yeah, we have a heat wave, and then we have the very high intensity of the sunlight. So this is very important topic to understand what is going on in Europe, what is going on in India. I think last a couple of months ago with the heat wave. So yeah. Oh, no question. So thank you very much. And then would you stop sharing your screen so Professor Qinyang Zhou can share his?
How do I stop sharing?
The button is like this below. Slow down. Go down to your Zoom. It's the icon in the middle of your screen. Go to the Zoom. No, the yeah, there, right. And there will be the button in the middle say stop. Yes. Oh, can I stop it for you? This stop. Okay, I will stop you. Eh?
Yeah, please.
Okay. Wait, I share something, and then wait, and I stop my. Okay. All right. Okay. Okay. Problem solved. Please, Professor Qinyang, share your screen now.
Yes. So can you see the slides?
Yes.
Yes. So good morning, everyone. I'm very happy to see you here, and I'm honored to have the opportunity to speak at this meeting. So my name is Qinyang Zhou, a doctoral student at Nanjing Agricultural University. So today, I'd like to present my topic with automatic phenotyping analysis of paddy rice panicle and the panicle developments on the nitrogen fertilization, treatments during the heating and the flowering stage. So in my report, it consists of these three parts. First one, as the figure shows, the growth duration of the transplanted rice. The reproductive pace started from panicle initiation, and in the early stage, panicles are hidden in the stem until the heating and the flowering stage. So it is an important stage in the reproductive pace. It is sensitive to external environmental factors, such as the temperature and the moisture, which is ultimately affected to the rice yield. And it is also the connecting link between the booting stage and the filling stage. The phenotypes on the flowering stage is not only the reflection of the growth and development at the booting stage, but also the characterization of ground quality during filling and sitting. But nowadays, studies on the panicle phenotype in the heading and the flowering stage, and manually focused on the plant panicle number, the heading date, and the flowering start time, estimating all the flowering time trees like flowering opening time, vigorous flowering time, duration from vigorous beginning to the end, and the rise, answer, and the stigma observation or its pollen vitality. However, visual observations and manual measurements are still relied on for such vital information on rice panicles phenotypes. This process is not just time-consuming, labor-intensive, and inefficient, but also the information obtained is limited. In large-scale field surveys, it is extremely difficult to obtain data due to the subjectivity of surveyors and the similarity between individual plants, and it is also difficult to observe a large number of plots simultaneously or with high frequency along with a time series. In addition, tracking the growth and the development of individual rice panicles and understanding the accurate flowering time trends, grain feeding indentation, all the other important information are still difficult to achieve manually. So in this report, we want to propose an automatic long-time series method to acquisition and analyze these important phenotypes. So our experimental is set on the southeast coast of China, and we use a solar energy field fixed platform with a 90-degree angle to take photos every 5 minutes automatically from the 8 o'clock to 18 o'clock during the whole heating and flowering stage. And for my workflow chart, first for the panicle detection, when we get the original images, we first cut them into sub-images, then we manually annotated the panicles label. Then we apply the Euro 5 detectors to realize the identification of rice panicles. And we use the detection results to complete the panicle counting and the heating stage estimate. Then for the detection results, we also cut them out, each individual panicles, and manually divided them into two categories. One is vigorous flowering panicles, and one is not vigorous flowering panicles. For the panicle classification, we use the Resonite 15 network model to accomplish the goal. Then, when we want to analyze a single panicle development, we need to check it from the beginning. So we take the images from the time series and integrate them into video, combine the Euro and the deep salt to complete the multiple panicles tracking, like this. Then the single panicle image with the same ID was cut out by the tracking results, and the images were put into the previously trained model to identify the vigorous flowering time panicles, so as to realize to analyze of different states of the same panicles in the whole heating and flowering stage. And this figure is the detection results display for 4 different treatment plots, include 2 years and 4 nitrogen levels. And when we tested the proposed panicle detection algorithm using 100 field rice images, and the results are shown in Figure 1. The R-score and R-E was 0.97 and 1.85, respectively. the accuracy of panicle detection models was more than 92%. And from the error values in figure 2, most of the values are less than 0, indicating that the model 10 is underestimated. So to estimate the heating date of rice groups, we first draw a dashed line at 50% of the maximum number of panicles for compression and draw the box plots for the data from the full treatment described above. This is the figure 3 shoe. When both the median and the mean in the box plot exceed 5% of the dashed line, the first day was recorded as the heating date of the rice population. Then we compared the full treatment heating date between manual inspection and our proposed method. The error in our estimated heating date reached 0.25 days. So our model showed good performance on the different nutrient application levels. Then, for the investigation of flowering time trees, we identified the flowering panicles from the time series pictures. We plotted the changes in the number of flowering panicles in days, and we also make the cumulative curve of flowering panicles number on the different nutrient fertilization treatments, which was shown in figure 5. So from this figure, we can see that with the increased amount of the nutrient fertilizer application, the flowering became earlier and the ending became later. The flowering duration became longer, and the daily flowering number increased faster, and the observed cumulative number of flowering panicles increased. So when we analyze the cumulative curve of flowering panicles number, we can see the increase in nutrient fertilization. So this may be reflected in two aspects. On the one hand is the panicles number increased, and the other hand is the flowering duration make longer. So according to the flowering stages of rice groups, there are differences in individual panicles. Just for example, the vigorous flowering time is different. Some will flowering at 11 o'clock and some will flowering at 12 o'clock. This has some impact on our calculation of flowering time. The difference between the individual leads to different flowering process, some of which are strong grains and some are weaker grains. So these are difficult to accurately analyze from this cumulative curve. Therefore, we need to locate and track a single panicle to improve the phenotypic information. Then we integrate the Euro5 and the deep salts and track the several individual panicles. The tracking result is shown as this video. Sorry, the video is not work. So we identified the flowering initiation days after transplanting, flowering days, and the vigorous flowering time, duration from vigorous beginning to the end, and the daily duration from vigorous to the end. And the results shows that the high nitrogen application leads to an early flowering initiation days. significantly longer the flowering days and significantly longer the duration from vigorous begin to the end. But the vigorous flowering time had no significantly differences, and there is also a slightly decrease in the daily duration vigorous from beginning to the end. So in our conclusion, we first proposed a method to automatically detect rice panicles in the field and accurately identify their flowering states. Then we accurately calculated the rice panicles number and identified the hitting dates of the rice groups. Then we analyzed the effects of different nitrogen treatments on the flowering phenotype of rice groups, which is in coding with previous research. In addition, we tracked the individual trends and the detailed phenotypes of flowering trees. Then the results showed with the increased amount of nitrogen fertilizer application, panicles number increased, flowering earlier, and the flowering duration became longer with both in groups and individual. And the duration from vigorous begin to end were longer, but the vigorous flowering time didn't change significantly. So that's all. Thank you very much for your attention and welcome to the questions.
Okay, thank you very much. Any question from the floor? I see the name of Professor Ninomiya again in this. So do you have any question?
No.
No. Okay. Anybody has any question? Okay, no. Nobody. Then thank you very much, Professor Qinyang. Oh, I'm sorry here because the pronunciation cannot, but thank you very much for your wonderful presentation. Would you stop sharing so Professor Abdul Lasak can share?
Yes.
Please, yeah, stop the sharing.
Yes.
Okay, Professor Abdul Razak, would you please share yours?
Yes, please. But this is very good morning. Professor, here is some internet issues. This is a rain. Maybe I'm connected all the way. Noise is a problem. So maybe sorry if we cannot continue. Maybe here is an internet issue, but I'm trying to connect.
Yeah.
So
okay. Maybe you try to share first. Yeah.
Is here in the morning.
Okay. If not, okay. Yeah, it's a kind of sharing. It might be difficult. Then would you send in your PowerPoint or that Sumi can share for you? Then the next speaker can speak first, and then you can follow that, because yeah, your internet you cannot share. I think it's not stable.
Yes, it's not stable. So actually,
yeah, it come now. Yeah, maybe I don't know. Maybe you send the maybe you can now. Try to go to the slide mode. Yeah, it's here. Your slide is here. Go to the slide. Yeah, share the full slide, please. Go to the first slide and share it, please. Then you can begin.
Okay.
Yeah, go to the full slide. Yes, it's here.
It's noise full slide.
Yes, the first slide already. But please hit the slideshow button in the bottom right. That you so we can see the full screen. or hit F5, it's okay. Hit the F5 key. Yeah, anyway, okay, fine. I just start yours.
Yes, thank you very much for giving me here. I'm thankful for the. So talk about the
okay. The problem is the voice. It's not really clear. So it's better you send the email of your PowerPoint to Sumi, and then we get the next speaker to speak it, and then the Sumi will run the slide for you. Is it okay? Okay, then you send the slide in, then the next speaker can in the meantime for the preparation, Professor Gandhi, would you please share yours? But he's not here. Okay. He's not here. Okay.
Yeah,
so we go to.
Yeah.
No, he's not here, right?
Yeah.
Right. Okay. Then the Professor Minomiya, would you please?
Okay.
While we're waiting.
It suddenly came. Wait a moment. I haven't opened my slide yet. So.
It's okay. It's okay. We have time. In the meantime, welcome. I saw Ken here. Oh, he left. Oh, yeah, Ken is here. He's feeling well now. Yes. Okay.
Yeah. Am I sharing?
Yes.
The slide.
Please.
Okay.
Yes.
Okay. So let me start. And good. Actually, Japan is already in the afternoon. And good morning, everyone. And I'm very glad to see the many of my old friends' names here on the list. My talk today is quite different, or totally different from those given by the previous speakers. Today, I will talk about a challenging policy of Japanese government about the agricultural production in Japan, which was announced quite recently. Not the result of my research, but just kind of an introduction to the policy of Japanese government. And yes, this slide shows one of the reasons why the government announced such a challenging policy. This is the so-called planetary boundaries defined by a Swedish institute about 10 years ago, defining 9 categories for the risks on this planet, such as the climatic change, ecosystem functions and land use, freshwater use, biogeochemical flows, ocean acidification, etc. And I don't think I have time to explain those things in details today, but unfortunately, agricultural activities are very much responsible for those risks. And very simply to say, the agriculture in this century or even the 20th century is not green at all. So having this kind of background, several countries recently have announced a quite challenging policy for the both productive and sustainable agriculture production, because still food is short. Food is, short. We don't have sufficient food, particularly having a quickly growing population on this planet. And for example, but at the same time, we have to secure the sustainability of agriculture production at the same moment. And for example, the Farm to Fork strategy announced by EU 2 years ago, and for example, it aims to 50% reduction of pesticide use. It's a big amount by 2030. And also they aim to reduce the usage of chemical fertilizer by 20% before 2030, etc. And also the Agriculture Innovation Agenda by USDA of the United States announced has been announced, which is also tried to achieve both sustainable and productive agriculture. But also, Japanese government announced a very similar strategy last year, named Green Food System Strategy. And this strategy is really challenging. Usually, you see that the Japanese government is quite conservative in making policies, usually, but this is really challenging. And this strategy for the green food system has 4 components: the production part, the supply part, the consumption part, and the processing and distribution part. And regarding the production part, for example, there are several actual goals. For example, in case for the smart cultivation, they aim to achieve 0 emission from agriculture sector, 0 by 2050. Actually, at this moment, the greenhouse gas emission from agriculture sector is about 25% of the total gas emission of the earth. And also it aims to reduce the chemical pesticide use by 50% by 2050. In case of the EU, that was 2030, but in case of Japan, that is 2050. And also they try to reduce the amount of chemical fertilizer by 30% by the same age, etc. Also, they are mentioning about so-called smart breeding, which can provide a very good cultivars or varieties, which can be optimized under the climatic change or with lower use of the chemical inputs, etc., while securing good productivity. Anyway, to achieve these goals in this strategy, yeah, we do need super innovation. Super innovation is necessary. Any of the current technologies we have cannot achieve those goals at all. And among that, in the strategy, it's said that the smart farming takes an important role. And let me summarize about the issues in agriculture in Japan. The first one is aging of the farmers and also the number of the farmers. The farmers' age, increases. The average age of the farmers increases almost 0.9 or something else every year. And it is going to be very close to 70 years old. They are very old. Also, we are short of the farmers as well. And as you see, the farm scale is quite small. In this graph, yes, in this picture, it shows this farm actually has 150 hectares of their land, but at the same time, they have more than 300 small plots. So the farming efficiency is very bad. And also, Japanese farming usually use a huge amount of chemicals and also uses a lot of energy. And also, the food self-sufficiency is very, very low as 37% this year. So now we do need to compensate those problems, to solve those problems. We do need a robotization and also knowledge transfer to the next generation, the farmers, and also we have to achieve the really sustainable production while securing the productivity. Now, I think this morning some other member of our laboratory used this slide, so I don't need to repeat the same explanation. But just this slide explain about the differences between the conventional farming and the smart farming. Like he said that there are 3 steps in the farming, in the cultivation. First they have to make a kind of observation in the field about the crop status and environmental conditions such as weather, soil, water, etc. And based on observation, the decisions are made. And finally, based on decision, the farm field management is conducted. And in conventional farming, everything is done empirically and manually and visually. So that these things are very, very inconvenient, subjective, and also labor intensive. While in smart farming, the kind of IoT sensors are used for the observation, and decisions are made based on the artificial intelligence, for example, and based on the decisions, the robotics or kind of navigation system, which can lead the human to optimal actions use. And they're all semi-automatic and accurate and efficient, etc. And of course, less laborious. And the largest difference between two types of farming is that something about knowledge transfer. Because in the conventional farming, knowledge is almost in the brain of the farmers. They are all tacit knowledge. So that it is very difficult to transfer the knowledge to the next generation. While in a smart farming, the knowledge is everything in the database, so that it is quite much easier to transfer that knowledge as a data to the next generation. But anyway, the smart farming can contribute to sustainability as well. And for example, of course, the smart farming can contribute to the higher efficiency of the production, but at the same time, it can contribute to the sustainability as well. For example, pinpoint pesticide spraying can reduce the amount of pesticide used in the field, so that also the cost of the pesticide can be reduced, because usually the pesticide is very expensive. And finally, it can reduce the chemical impact on the environment as well. The same thing happens when we conduct a variable fertilizer application in the field. The crop does not grow homogeneously, so quite heterogeneous, so that the fertilizer should not be equally applied to the field. Just observing the growing stage, then the fertilizer application, amount of the fertilizer application can be optimized, so that finally the amount of fertilizer can be reduced. Also, at the same time, the cost is reduced, and of course, the impact on the environment is reduced as well. So, having looking at such a benefit of the advantages of the smart farming for productive and sustainable agriculture, the Japanese government announced the smart farming verification project. It started in 2019, and this is kind of demonstration project. And the government subsidized smart farming equipment to the farmers. And the objectives is to introduce advanced technologies such as robotics, AI, IoT, etc., into the actual production site, farmers, farm companies, to verify the effect of management improvement. And also they promote smart farming support services such as machine sharing and interoperable data platform, etc. And so the farmers, the government subsidized farm management information system, robot tractors, robot transplanter, automatic water management systems, and drone monitoring systems, or drone pesticide spraying systems, and robot harvesters, etc. And during this verification project, 179 trial cases, farmers are selected under the various different conditions regarding farming scales, farm products, terrain types, climate types, not only for the big scale farmers, but also very small scale farmers joined in the mountainous area of Japan, also joined this project. And say, for example, the paddy rice farms and fruit farms, outdoor vegetable farms, and the tea farms, sugarcane farm, livestock farms, etc. And some of the results, still the project is going on, but some of the results just started coming. For example, by using drone pesticide spraying system, the 80% of they can reduce the labor time by 81%. It's a tremendous effect, with the same pest control effect. And also automatic paddy water management system can reduce the 80% reduction of labor time, because usually farmers, as I have shown you, many of the farmers have many plots, 300 plots or something else, and they have to control the water level of each of the plots. They have to go around the paddy field, so it's really time consuming. But using this automatic paddy water management system, we can reduce the huge amount of the labor time, for example, etc. And in addition to subsidizing such smart farming equipment, they're also promoting the smart farming support services. Smart farming equipment is still quite expensive, particularly for small-scale farmers. So, for example, they are promoting to smart farming equipment sharing services, so that the farmers can share smart farming equipment, robot tractors, etc. But also, they are promoting to start smart farming operations agencies. They can operate the drones and drone spraying management, etc. And also promoting smart farming equipment rental services, so that those farmers can rent those equipment with quite low cost. And also we need to, smart farming is quite new to most of the farmers in Japan. We need to raise the kind of literacy of the farmers. So the government, this project is promoting the public training and education program for smart farming literacy to the farmers. Now, in addition, the national platform for smart farming, kind of interoperable data platform, has been provided and being developed. The system is named Waguri. Okay, so in summary, just very challenging. The green food system strategy Japan was announced, as other countries also done. I don't have much idea about other countries, but anyway, this is quite challenging strategy. And to achieve this very challenging goal under the strategy, the smart farming is really will take an important role to achieve some of the strategy announced under the strategy. Okay, that's all. Thank you very much.
Okay. Thank you very much, Professor Ninomiya. The Wagri, right?
Wagri, yes.
Wagri, yeah. I try to contact them because the NECTEC in Thailand, they're doing agri-map, and then they would like to copy or whatever for Thailand, for the whole country, but it turned out to be like under license or something that cannot share. So it's so unfortunate. So
yes, there are still several problems, and they have been trying to. I mean, this is the first time for them to have this kind of service to share the data, and particularly they are focusing on. I mean, they have understood the importance of the kind of common standardized APIs to share the applications and the data. But of course, the data and applications cannot be totally free.
That's the thing, right?
So I mean, yes, there are some difficulties, yes. Yeah, but I think it's a good idea, because we should not make this system just within in Japan, but we should share the system among at least among the Asian countries, where the same kind of paddy rice is quite common among us. So. Yeah, we should share it. Yeah, always I
hope they could share, because we try with Naro too, and then they direct us to the Keio University who developed it.
Yeah,
and it turned out that cannot share. So I think that was maybe last year, 2 years ago. And now Thailand need to find other way to do it, because they need to move forward as well.
Oh, I didn't know that. I didn't know that.
Sorry, it's fine. I'll ask the guy who do it.
I know many people from the project, Wagri project, and we've been discussing a lot. And I feel that is getting better now.
Okay, because I think that the why we ask at the beginning, because if we could have the similar system or the same system, then in the future we can integrate. You know, we thought like that, but it turned out like
yeah.
So yeah, because in the future, yeah, and then it turned out to be this data issue that when they collect them, it costs money. So it's not simply to share. Then even though we said that we don't need the data or anything from Japan, we just need the framework, you know, how you do it, then we can develop something similar that in the future we can integrate together if, you know, like if the opportunity allowed it. But it turned out that they couldn't even share how they have the framework of the system.
Yeah, actually, the Wagri itself doesn't have much data in it, but they provide a kind of interface to access the various distributed databases. So the idea, the idea is a bit different from, you know, they are not developing a huge database, but just developing kind of standardized gateway to distributed data and distributed applications.
Okay.
The idea is not too bad.
Right. Because for this Thailand system called AgriMap, it's just like linked to the funding. I don't know, from the government, that the farmer can identify what they would like to do, what kind of crops, and then is it match the quality of the soil, the quality of the water around them, something like that, and then they can get some loan from the government for the certain crop types, but if not, they cannot get it.
Maybe, you know, we can organize an international workshop, something else, to share the kind of ideas about kind of data platform among the different Asian countries. Okay, I will try to discuss with it.
Yeah, because here Professor Wang also Wang also said that it's difficult to get the framework or the source code, and then and then we are moving to this open and sharing effort that we're trying to do. So it's very difficult. Please, Adi.
Yeah, thank you, Zhang. Ninomiya-san, it's always, you know, very informative talks that you give it in any platform you take it. Thank you very much for this. First of all, you know, many countries, particularly the Asian countries, the data policy is not that good to share. So does it solve the problem to have it open data? That's what the Chai-san is also mentioning, as we have seen yesterday also in the APAN. A lot of these open science systems are coming up. So will it help us in reducing some of the gaps that you mentioned in your slides? Yeah.
Yes, thank you.
Okay. Yeah. Oh, okay. It's the file sent in by the Professor Qinyang in this in the chat box, so you can save it, I guess. But yeah, it's kind of a big issue with it open science that they're trying to do, that for the sharing information and data, because those costing money. And even the yesterday or 2 days ago, Jenny from University of Indiana also like said that in the US that NSF now they changed the rule. If you want to get funding, you have to share data. If not, they're not going to give you any money. So that's the way it is in the US now. And then but maybe please.
Yeah, also the JST, it's a very similar organization to NSF.
But
also requesting us to share the data. Yeah.
Right, but that in the future data you collect, not the old one. The point of sharing data, the sharing data is that you don't have to do the duplicate stuff, and you can go forward much quicker. But no. I really don't know what to get this problem, the pain point away. Anybody have any idea?
Actually,
we try to do it. We're trying to do this in the APAN community. That while starting now, maybe you notice a little bit that we will launch this data.apan.net. So each working group will contribute to this. Like our horticulture working group will share what we can to do, like the free data, free information, or even free training regarding the agriculture into this web portal. So the APAN community will be much easier for doing the research.
Yes. Kind of the top-down process is approach is very difficult, but maybe the bottom-up approach can realize some part of things like us. So maybe you can organize a very special session for the data sharing or something else. Actually, I know that these kind of things have been discussed everywhere for many
we
years.
Have a working group now in APAN. We have a working group for it. Because of it started a couple of years ago because everybody complained, and then about this sharing of trying to get information on data to do the research. So we have been discussing within the group, and then said that maybe APAN could do something because we have so many NRENs as a member.
Yeah.
So and then many institutes. So we will try. And then the beginning now, the NII from Japan kindly support to develop the system, but it will be, well, all the system they developed or the function within the website, but it will be based in the APAN itself. I mean, APAN, I don't know, cloud they use or the server that they have itself. So within APAN community, we can at least start by sharing each other first, and then helping from each working group to share this. And then we invited the UNESCO to join us again, because they also have this open science going on. And then the China, I don't know, they also have the same thing that trying to do Australia. So hopefully we can share more, because that help a lot. If not, okay. Anybody would like to answer this? That do you have a public data server by a government supporting in the, here in Malaysia, Suhaimi have it? In Thailand, I'm not sure, but we have the central server that the government by NECTEC, the National Computer Center, and with the different agencies sharing data that they can. For example, this agri-map that you can just go into the system and tell that for your property that you have or your field, which okay, my internet not good. Which crop is suitable for your land, by sharing the data from like soil data from the Land Development Agency, and then the variety of information that we could. But this agri-map system is not really up to date. That's why we would like to use the similar system at the WAGRI, that we can support, I mean, update it more and more frequently. Yes, in the chat box, Mia Sensei sent in this what is it, RDA, I mean, Data Alliance. We try to engage with them as well. And then I think a couple in Indonesia, APAN 52, we invite them to speak. And then and they also have this APAN have this MOU with the, I don't remember the global agricultural group. I don't remember the name.
Yeah, Godan. I put.
Godan. Yes, Godan.
Yeah.
Yes, but they never show up last time.
No. I mean, they disappeared. They've been supported by FAO, but recently, just I think resolved. I haven't received any information.
Yeah, it's strange.
Yeah, RDA is still active, but still, I mean, lots of discussions, but no solutions.
Yeah, he disappeared, and then he sent some member from Godan to be in the mailing list from the open and sharing data, but they also not respond. Like, I don't know what happened. And trying to reach him, he disappeared too. So I don't know. Yeah. Okay. The Professor Abdul not coming back, so I don't think we have any more speaker. Then we are in the discussion session already now. Any particular topic or anything that you would like to discuss, please. Okay. Ken, are you still there? Okay. Well, then it's quite of a I don't know, for this open and sharing. Hopefully, after we launch it, I don't know that anyone here would kindly provide any link, any training link or whatsoever that could be shared, that sent to the APAN sec, and then or we will have a new email address. I'm not sure that I get confirmation from APAN sec that is already working. It said data@apan.net to send the comments or whatever you would like to put in this website, because it's not fair. I said that as the at the beginning NII of Japan, they thought that they have to do by themselves. I said no, that's not the way. We have to help each other, because it's that's the way we would like to see, not you doing it only. So please, and Eric too, yeah, for disaster mitigation, would you please get this useful link or whatsoever that you think that can be shared? Okay.
Sure, I will. Yeah, if I may, about the open data or open science, maybe the tools for either for the processing or analysis data should be also taken into account, rather than just data, but also the tools. That will be also helpful. Yeah. The other way is maybe we could focus on those data or tools, which has been published. I mean, there is a paper has been published. Then we can focus on those cases or projects. The publication has been accomplished. Maybe that will be easier.
Yeah. Just send in those, and then we'll add it into the website that will be launched. This is a draft one, version 0, I can call it, but we aim to finish it at the end of October. Then we'll see that how it can develop. But before that, please send in as many as you could.
Yeah.
You know.
Sure, I will. Anyway, the open data is a very, very valuable initiative in Asia through APAN. Yeah, very nice job. Thank you.
Okay, all of us have to help each other. That's the thing.
Eric, any discussion in Taiwan as well?
In terms of agriculture?
Yeah, not any sectors.
Yeah, yes, for the at least for the biodiversity and ecology related researches, the funding agency enforce the policy. If the data is not open, then it's not possible to get funding. A very similar policy as you mentioned in Japan and also in NSF. I think that's the that's the common strategy from the funding agency.
Yeah, right.
In Academic Sinica, we are trying to promote and also deploy those open data and open science infrastructure, the platform to the academia in Taiwan. Yes, but it's not easy. That's why I like to suggest from those projects which publications has been announced or released. Starting from those projects will be more feasible, at least in Taiwan here.
Okay, thank you very much.
Yeah, thank you.
Okay, I see that Eugene from TNCC is here. There's a fun, I mean, is that the same policy going on with TNCC? That you have to share everything as well in order to get funding?
Yes, for all the data should be shared if it is funded by any organization or government. So it is the same as the Asia Connect. Yeah.
Okay, now it's kind of become the standard that everybody need to share in order to get funding. Well, good. So, okay, then I hope all of you or most of you will help us develop this, well, I don't know, database to be utilized for everybody in terms of data sharing and then information open science. We're trying because the climate change is moving so fast. It's a drought everywhere now. The Europe announced that they have 500 years drought. China just got hit by the heat wave, and Korean got big flooding. And you know, I don't know, Pakistan, I mean, not here, also just got big flooding, something like that. Everything changing so quickly. Please, Aninomiya Sensei, please.
Yes. No. Just yeah, unintentionally, I just turned on the microphone. Maybe I was saying something else.
Okay. That. What about Hattori Muffin? What the Muffin thinking like near that? Is that anything open and then sharing scheme within the Muffin? Oh, okay. Hello, NICT. Do you have this kind of initiative to open and sharing your information or data or technology? You know, no. Well, okay. Then Suhaimi, are you there? Okay. Okay. Then any last words for the session? Okay, Kitty Pong, would you like to take photo again? Oh, no need. No response. Am I alone here?
Yeah, maybe we can take the photo.
No, it's up to you. It's just like
yeah. I see some new participants.
Yes.
Okay. Okay.
So maybe you can combine. Yeah.
Yeah.
Two photos.
Okay. Hattori is still here. What about Muffin? Have Muffin doing anything with this open and sharing? No, not really. No, or just try to start. Okay. Then we take photo then. Okay.
Okay, 1, 2, 3. Yes.
Okay. Any last word before we close the session? Okay, if Ninomiya Sensei, any last word?
Not particularly. Yeah, thank you. Yeah, thank you very much for sharing. And yeah, I love that kind of discussions. That was very good. And also there are lots of very nice presentations.
Yeah, indeed. Very moving forward. Yeah, we need to really do it, I think, with the food security. As a question also, I need to maybe one more question for you. I heard that maybe 10 days ago something that regarding the soil health with the fertilizer. How do you know how much you put in to still keep the soil healthy? Maybe you put too much, maybe you put too less. So do you have the answer for that? Like, I don't know. So do we have the answer for that? That how much we can put the, I mean, I don't know what kind, whatever the.
Well, that is yes, should be much lower than what we are using right now. I mean, and now, for example, last year it's really nice wheat, not the cultivar, still not yet, but a very good discovery was announced that a wheat cultivar does not require as much fertilizer as before. So that can grow. I mean, with the same productivity, without less input. So that kind of invention can take place.
Yeah, right. Because now they're talking about the carbon trade or something. Now you need to know the soil carbon, something to add to, something like that, and we don't really know that.
and also less water.
Yeah.
Drought resistance and many things are just many studies, researchers going on. So we should expect that they will achieve some of the goals.
Hopefully.
Otherwise, we cannot survive.
Yeah, that's
not ourselves, but some
species, not us. Some species will like mass distinction that they keep talking. Because one guy from, like I said in the previous session, from WHO that I know, he's so afraid of it. That's gonna be the mass extinction, and even our kind will be, I said, well, we survived for a million years. Don't worry about that. But he's still worrying that the food is the problem. Like for the greenhouse gas, most of the, I think that now they have the number. The greenhouse gas contribution is from agriculture. Actually,
25%.
Yeah, the most from agriculture.
Not most, but 25%.
Okay. But I thought that what they said now, the new one to do is like to do the more efficient agriculture, because maybe they combine with the deforestation. Maybe right, deforestation that's happened not because of the forest fire. Not because of any disaster, it's just because of the agriculture business that's destroying this forest. For example, in Amazon forest, there's a lot related to this agriculture business. So right, wrong. Yeah, right. The agriculture contribute to deforestation. Yes.
Oh yes.
Yeah. Anything else? Okay. If not. Thank you very much for coming, and then for all the contribution. Don't forget to share your PowerPoint so they can put in the APAN website that everybody can access later. And thank you very much, and see you in the APAN 55 in Nepal. Hopefully, face to face if possible. Not another wave coming. Yeah, and take care, and then thank you very much. Thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you very much.
Thank you. Bye-bye.
Thank you.
Thank you.
Thank you. Bye.
Bye bye.